As I told you, Luis is the coordinator and the real, the person that make possible to have this locomotion project. And especially that many researchers meet together during these 4 days, for years beyond, the work that we have to do, I think was really a good experience of life for all of us. So please, Luis, the floor is yours.
Thank you very much, Simone, for your kind presentation. I'm going to share my screen. I hope you can see my screen now.
Perfectly.
Okay. So, well, thank you again to everybody for attending the course and the organization by University of Pisa, and especially Simone and their team. I'm going to give you a short presentation about integrated assessment models and system dynamics. Obviously, it is going to be a very simple introduction with the key concepts. Maybe most of you are familiar with that, and maybe you don't need it, but I should start with a very simple ideas to be clear what are going on in the next days with the WILIAM model and so on. Well, as Simone said, I belong to the University of Valladolid. In particular, I am a member of the group of energy economy and system dynamics of this university. Wait a minute. Okay, so this is part of the locomotion project. In the locomotion project are involved a lot of partners, about 13 partners from different countries, including University of Pisa, University of Valladolid, and other partners that you will know in the next days. It has been a project of more than 4 years, so it has been a big work, hard work, and now we have some results. We are trying to explain you. So let me start with a little bit of history. In 1992, this is 1 year that maybe some of you haven't been born yet, about 1,700 of the world's leading scientists, including most of the Nobel laureates in science, published a letter that is called, it was entitled World Scientifics Warning to Humanity. This is about 30 years ago. And in this text, we can read something like, we must bring environmentally damaging activities under control to restore and protect the integrity of the Earth system we depend on. Also, we can read another sentence like, we must move away from fossil fuels to more benign and unsustainable energy sources to cut greenhouse gas emissions and the pollution of our air and water. Also, we must halt deforestation, injury to and loss of agricultural land, and the loss of terrestrial and marine plant and animal species. However, during the last 20 or 30 years, the CO2 emissions has been increased nearly every year, with some very special exceptions with the COVID, the global financial crisis, and so on in these points, but we have been increasing all the years the CO2 emissions. The results obviously has been an increase of the atmospheric concentration of CO2 every year that we haven't been able to stop. Obviously, it has been due to the use of mainly, not only, but mainly to the fossil fuels, and the oil consumption, coal consumption, and gas consumption has been increasing during the last years with these exceptions I have already mentioned, while renewable energies are still, let's say, less important in the energy mix. 25 years later, in 2017, World Scientifics again published a new paper entitled World Scientifics Warning to Humanity, a Second Notice. In this case, it was signed by more than 10,000 scientists, most of the most relevant scientists in that time, and they noticed that most of the indicators that in the first warning was noticed were indeed worse than 25 years ago, with the exception of the ozone depletors. For the rest of the indicators, like freshwater resources, marine catch, vertebrate species abundance, total forest, the zones, and obviously the CO2 emissions and temperature change, the situation is now, and it was in the 2017, 17, worse than and it was ever. So obviously there have been more warnings to society coming from different scientifics. Maybe one of the more well-known is the planetary boundaries developed mainly by Roston and Christine in the Stockholm Resilience Institute. But the question is, the question I would like to give you is about why has society not been able to react in time to the warnings from the scientific community and reverse the evolution of the environmental damage on the planet? So probably you will have different opinions about what is the reason that most of the scientific warnings have not any kind of impact in the society, maybe due to the politicians, maybe due to the human behavior, but the results, as you have seen, are really pessimistic. So I don't know exactly what is your opinion about that, but anyway, it is a very interesting area of research. This is our research will be the relationships between science, technology, and society. Unfortunately, we are not going to talk about this very interesting area of research, but maybe one of the answers to this question is related with the complexity of the problem. Why the problem is so complex? The problem is so complex for many reasons, but maybe the most obvious is because there is a large number of factors. We are about 8 billion people in the planet. So, and the human behavior of each of us has influence on the environmental issues. So it's quite complex to understand how is going to be the things depending on so many actors. Another reason of the complexity is the multiple relationships between variables. And some of these relationships between variables are nonlinear, represent some feedbacks, and obviously there are a lot of uncertainties in these relations. We cannot predict the relation of the behavior of the variables. So what we need is a holistic view of the problem. Probably many of the people, many of the scientists, many of politicians focus the attention on some of the issues that are related with the environmental problems. For example, many people focus attention on technology, and they said, okay, technology is going to save us from all the problems. We need to develop, let's say, more renewable energies, more efficient energies, features, or maybe some other people focus attention on economy or maybe human behavior. We should change our human behavior related, for example, with diets, with our consumption. We need to reduce fossil fuels. Maybe we need to keep the forest, or maybe we have to change the land use or whatever. However, it's not as simple as focus the attention of one of these issues. The problem is just a global overview of all these variables, and of course, much more than I can represent here in this diagram. And we need to take into account all the variables, and we need to take into account all the relation between these variables. Obviously, this is a very complex description of the problem, and we will need to have something like that, something like try to classify in boxes all the variables related with economy or population, all the variables related with energy, all the variables related with climate, all the variables related with social and environmental impacts, or something like that. And obviously, all the relations between all these kind of boxes. So this kind of holistic view of the problem that we need to do is in order to, first, to understanding the problem, variables involved and all the relationships. And we need to understand the problem because we need also to make decisions knowing all the consequences, not the short-term consequences or the consequences on maybe environmental, but also on the well-being of the people and so on. So this is the background of the need of integrated assessment models. What we are going to try with an integrated assessment model is just to put together all these, let's say, knowledge areas, variables, and try to understand what is happening inside. Well, more formally, an integrated assessment model is a mathematical computer model that integrates economic, technological, environmental, and social variables in order to understand the effects of some variables on others and help in the political decision making in these areas. Sometimes the integrated assessment model are focused mainly on energy, economy, and environmental models. Then we call sometimes E3 models, economy, energy, and environment. Usually they are highly complex models because there are several interrelated models, thousands of variables, parameters, feedbacks. We are talking about maybe even millions of variables and so on. Some of the most well-known integrated assessment model are World 3. Historically, maybe it was one of the first, very well known because of the limits of the growth book and the work of Meadows and more people. DICE, one of the first integrated assessment model. Image, DCAM, Pulse, Magic, Merge, Gini3, Message, Remind, Which, WILIAM, and obviously there are much more. And more recently, we have been working in our group in Medea's, Eurogreen, or WILIAM. WILIAM is going to be the focus of attention of this course, and we will explain, Inigo will explain later the reasons of the novelty and interest of the WILIAM model. Well, integrated assessment models aim to provide policy-relevant insights into global environmental change and sustainable development issues by providing a quantitative description of the great processes in the human and the earth system and their interactions. This is the key issue. So, some common purpose of the integrated assessment model, IAMs, are to provide a coherent framework for organizing and assessing knowledge about climate change, to assist in the assessment of the consequences of different policy options, to understand which of the many uncertainties about the modeled system are most important. We are going to see in the lab practice probably these kind of issues, and to better understand the interaction between the components of the modeled system. For example, economy, technological, and environmental subsystems. How do integrated assessment models work? So, usually we have a computer model. This is the green black box, in which we have a lot of equations, usually different differential equations, or maybe algebraic equations, whatever, that establish the relation between economy, energy system, consumption, production of energy, whatever, the land system, land uses, forests, crops, production of any kind of land product, etc., and climate. The climate by itself, CO2, but other greenhouse emission, greenhouse gases. So with this, let's say, complex model, we need inputs. The inputs usually are some kind of exogenous inputs that affect, obviously, to the model. Some kind of these inputs may be GDP, population, policies, and some kind of other hypotheses or assumptions in order to run our model. And obviously we will have outputs. The outputs are the variables that we want to focus the attention, and the variables that will help us to take decisions. For example, any kind of economic outcomes, emissions, energy pathways, land use, whatever. The inputs of the model, usually we call scenarios. Scenarios will be this kind of, let's say, external or exogenous variables, inputs that we are used to introduce in the model as inputs. So in order to run the models, we need to define the values of these kind of inputs that we call hypotheses and policies that define a scenario. The scenarios are a key point to be able to properly use the models. Some families of global scenarios use it that maybe you will know. For example, in the IPCC are RCP, representative concentration pathways, SSP, shared socioeconomic pathways, and SPA, shared climate policy assumptions. They are more or less common families of global scenarios that international organizations and entities use in order to give inputs to the models. In particular, socioeconomic scenarios are plausible representation of the future based on coherent and internally consistent assumptions about the evolution of the key social and economic drivers. Clear examples of these drivers may be economic growth, technological development, so how is going to be the technological development in the next years, population, the same question, how is going to be the evolution of the population in the next years. They are not intended to be predictive. Nobody knows exactly how is going to be the number of people, the population in the next years, but are designed to explore the implication of different possible features. What does it mean? For example, let's say that we will design a scenario A. Scenario A may be how is going to increase population, how is going to be the improvement of technology efficiency, whatever hypothesis about regionalization or globalization of the trade. So with this scenario and with the model, we simulate for a time and we obtain, let's say, a future projection A. This feature projection is not the prediction of the feature, it's just a projection. Are expected results for this scenario and its policies. Its policies related, for example, about mitigation or adaptation policies for climate change. The same we will be able to do with a different scenario. Scenario B with another hypothesis, another different policies, the same model, same simulation time, and we obtain a different future projection, let's call B, and the same for C. So we will obtain, in this case, 3 different projections according to 3 different scenarios. What we are going to do with that? We are going to compare what are the implications of each scenario, what is the implication of each hypothesis, of each policy, in order to observe in a more qualitative way, more qualitative than quantitative, what are the consequences of our policies, of the consequences of different hypotheses. The integrated assessment models are used then to answer a series of what if questions. What if population increase a lot? What if population increase only a little bit, for example? What if we apply this kind of international policy? What if we don't apply this policy? This kind of, let's say, methodology, we call a scenario methodology, and is a method to deal with a large uncertainties. So we have results for different possible features. And it led us to develop a comparative analysis. The feature obviously cannot be guessed. The different trajectories of possible feature projections are compared, and we compare between these trajectories the advantage as disadvantage. So briefly, integrated assessment model are computer simulations models. They can be programmed with any modeling method. For example, maybe some of you will know agent-based modeling or whatever. And any computer programming language. You can program integrated assessment model with Python, with C language, with GAMS, with whatever. Okay. In our case, we are going to use system dynamics approach, and we are going to use Benzene software. Just to mention that there are other relevant software specialized for dynamic software, for system dynamics, sorry, like Stella and PowerSync, but in our case, we have chosen Benzene. So in the next slides, we are going to talk a little bit about system dynamics approach and just a little bit about Benzene software. So system dynamics is a computer-aided approach for strategy and policy design. So it's more or less suitable for the problem we want to work. The main goal is to help people make better decisions when confronted with complex dynamic systems. The approach provides methods and tools to model, analyze dynamic systems. Model results can be used to communicate essential findings to help everyone understanding the system's behavior. It uses simulation modeling based on feedback systems. The feedback is going to be a key idea in this kind of system dynamic approach, and it complements with system thinking approaches. Maybe some of you are familiar with the system thinking approaches. It applies to dynamic problems arising in complex social, managerial, economic, or ecological systems. It can be applied to social, managerial, economical systems and philosophical, physiological systems. So just some quite relevant milestone in the history of system dynamics. Maybe the starting point of the system dynamics is the general system theory that was developed in a book by Ludwig von Bertalanffy in the middle of the 20th century. At the same time, more or less, Professor Jay Forrested, this is considered the father of the system dynamics. He belongs to the MIT Sloan School of Management, developed the basic tools for the system dynamics modeling, and he published some books about industrial dynamics, urban dynamics, and other books. At that period, there were developed the first modeling language for system dynamics that they were called Sample and Dynamo. They are the origin of the software that we have mentioned before about Benzene, Stella, and PowerSync. And maybe one of the most relevant, well-known milestone for system dynamics was the work of limits to the growth that was done by Donella Meadows, Dennis Meadows, and Rangers by a work by the Club of Rome. And they developed a world model that it was called World 3, that was probably one of the first integrated assessment model, more or less simple, but very intuitive. And even with the revisions of this very old model, they were being able to predict in some way the actual situation, the nowadays situation. So the starting point in modeling with system dynamics usually are the causal diagrams. Causal diagrams are qualitative relations between variables we want to model. This is a very simple example. We know that the CO2 in the atmosphere, the concentration of CO2, increase the greenhouse effect. The greenhouse effect increase the temperature, the global temperature of the planet. The global temperature increase the desert expansion. The desert expansion decrease the photosynthesis of the plants. The photosynthesis of the plants increase the CO2 in plants, and the increase of the CO2 in the plants will decrease the CO2 in atmosphere. So we have a complete loop with 1, 2, 3, 4 positive relations and 2 negative relations. In this kind of causal diagram, we only express the positive or relative relation between variables. We are not talking yet about equations or something more complex. Just, let's say, an intuitive or a clear relation between 2 variables in any terms. Let's give you another example. We know that as far as we have economic growth, the economic growth usually leads to an increase in the energy consumption. We need energy consumption for energy economic growth. As obviously also, if we have energy consumption, we increase economic growth. So there is a feedback loop, a positive feedback loop that we can understand. For example, if we check the data, the historical data of the world energy consumption and the GDP growth. In the graph in the right, you see how has been historically the increase of the global energy consumption and the global GDP growth during the last historically in the last years. Obviously, the relation is much more complex. We can continue with this causal diagram, and we can observe that we have energy availability. Energy availability means that energy have some limits. So as a consequence of the energy availability, we will have that energy consumption and energy availability will produce energy shortage. This energy shortage will produce a decrease of the economic growth or economic degrowth. So in this case, we have one positive feedback and one negative feedback. The negative feedback stabilizes the situation, is a stable situation, while positive feedback produce exponential growth. So we can continue with this kind of causal diagrams. The next step will be, for example, to understand what is the energy availability we have. The energy availability will depend on the non-renewable energy, fossil fuels, uranium, and also from renewable energy. As much renewable energy we have, as much non-renewable energy we have, we will have more energy availability. But both non-renewable and renewable energy sources have some physical limits. So we need to consider the physical limits in order to determine the availability for non-renewable and the availability for renewable energy. So finally, we can mention that in the last years, the energy shortage has led to increase the effort to develop more renewable energy. And we can continue with this diagram. This is only an example. Let's say if we introduce more variables, we can introduce variables like the infrastructures for renewable energies. We can introduce the important variable of climate change. As we use more non-renewable energy fossil fuels, we will have more climate change. More climate change will reduce the economic growth. The climate change will promote the increase of new infrastructures for renewable energies. If we have economic growth, we will be able to increase also the infrastructure for renewable energies, and so on. We can consider other variables like, for example, investment in research and development. It will be possible if we have economic growth. We do bigger investment, and usually it will lead to technological improvement, and it will improve the GROI. And well, this is something that I am going not to get deeper, because you will get deeper in the description of the WILIAM model. So this is a starting point anyway of system dynamics, a kind of, let's say, conceptual overview of the relations between variables. But obviously we need to get in a more, let's say, mathematical relations. We need to describe these variables in terms or something quantitative variables. So in order to change to let's say mathematical quantitative variables, we are going to use mainly two types of variables. One of the variables are stocks, and another variable are flow. Stocks are accumulations. Accumulations mean that they are able to characterize the state of the system and generate information upon which decision and action are based. Stocks usually have inertia and provide some kind of memory. A clear example of a stock is the CO2 in atmosphere. CO2 in atmosphere is not going to change quickly. CO2 in atmosphere represent the history of all the emissions and absorptions in the last years. And obviously it has inertia and memory on the past. This is a, let's say, a state variable, okay? And the other kind of important type of variable are the flows. The flows are variables that are the derivatives of the stocks, how the stocks is going to change, maybe inflow or maybe outflows. In this case, the stock of the CO2 in the atmosphere change due to the CO2 emissions. CO2 emissions is a change in the CO2 in the atmosphere and the CO2 absorption. So we have two flows in this very simple example. CO2 emissions is a input flow, inflow, and CO2 absorption is a output flow. Another classical example to explain stock and flows is about population. Population may be human population or rabbit population or whatever, have usually two flows, births and deaths. So population is the stock, is the memory, the accumulation, the inertia, and it increases with the births and it decreases with the deaths. Mathematically, it will be the population at time t will be the population in the previous time, t minus 1 of population at time 0, plus the integral between births minus deaths along the time we are considering. And the variation of the population along time will be the difference between the births and deaths. So it's clear this kind. Another example, in this kind of example, we have two stocks for the rabbit population and fox population. We have 4 flows, rabbit bears, rabbit deaths, fox bears, fox deaths, and obviously there are other variables. The rest of the variables we will call auxiliary variables. Auxiliary variables are not involved usually in differential equations, are only algebraic equations, algebraic relations. And in this case, for example, the rabbit birth rate will be an auxiliary variable, the initial rabbit population, and the same for foxes. We have in this case the carrying capacity. Carrying capacity is the limit that we are going to have for rabbit crowding. And of course, we have a relation between the fox population and the rabbit population. As fox eat the rabbit, the fox consumption of rabbits will be a relevant variable in order to define the rabbit deaths, the natural death and the rabbit that the fox ate. Okay, this is just an example, an overview, how are the appearance of the system dynamics model. This is another part of the model. In this case, this is part of the World 3 model I have mentioned before. And just to focus attention that we have here 4 different stocks: potentially arable land, and urban and industrial land. So we have flows from arable land to urban and industrial land, from potentially arable land to arable land. We have flow because we have some lost due to the land erosion rate. And well, and here we have the land fertility. We can increase the land fertility due to the regeneration or degradation of the land fertility. This is different examples of stocks and flows. This is a real example from the World 3, as I mentioned before. This is the last example. This is a famous example of the COVID epidemic. Well, it's able for any kind of epidemic, but it was developed by Fidaman specifically for COVID. And in this case, we have people that are susceptible to be infected, people that are exposed to COVID, people that are already infected. Some of the people infected dead, so go to the number of deaths, and some people infected after recovering is recovered. So in this case, we have 4 stocks and we have different flows: infecting, advancing, recovering, dying, imported infected, and so on. And we have a lot of, let's say, auxiliary variables like hospital strain, import time, transmission rate, initial population, seasonal effect, and whatever. So just an overview about what is the, let's say, the appearance of this kind of system dynamics models. So some relevant characteristics of modeling basis system dynamics that we have to take into account. System dynamics models are characterized because they are transparent models based on causal relationships. The opposite will be that it is called black box models. Black box models, we don't know what are inside. For example, a classical black box model are those that are built based on artificial intelligence methodology. You know that the things are working because they use many data, but you don't know exactly why this is the output or the input. So this is a black models. In our case, models should be completely transparent. We need to understand the causal relationship between variables. They are oriented to represent feedback relationships. I have shown some kind of feedbacks, but any kind of system dynamics model have always several feedbacks, or nearly always. It allows representing nonlinear relationships and delays that are quite important in the real world. Models should be conceptually simple to understand, so we need to understand what they are doing. Nothing gray, nothing strange. We need to understand physically. It allows you to integrate variables from different areas of knowledge. I explained how to relate economy, climate, and so on, different kinds of variables. Allows modularity of the models, and it is suitable for working with uncertainties. There are specific tools to analyze uncertainty in the model. So these are the most relevant characteristics in order to work with systems dynamics instead to use any other kind of methodology that we'll be able to use. So obviously there are a lot of bibliography on systems dynamics, but in order to learn about system dynamics, let me recommend you a couple of books between all the books that you will be able to find. One is probably one of the most well-known book by Sterman, Business Dynamics, System Thinking and Modeling for a Complex World. And the other is by Andrew Ford, Modeling the Environment. And you can find a lot of resources for System Dynamics courses and materials, books, and so on in the System Dynamics web of the System Dynamics organization, the society, sorry. So this is the web page of the System Dynamics society. So, and finally, in order to finish this part, what is benzene? Benzene is a visual modeling tool that allows you to conceptualize, document, simulate, analyze, and optimize models of dynamic systems. Benzene software provides a simple and flexible way of building simulation models. From causal loop, we can start just with the draw of the causal loop, or we can start with the stock and flow diagrams that are the kind of diagrams I have already showed to you. It's a commercial software by Ventana Systems. All the information about benzene you can find in the web page, including the downloading of the free versions. Globally, there are many different versions of benzene software. First of them is the PLE free for academic use. This is the version that Simone mentioned at the beginning, and you have in the documentation of the work of the course. You can download in this web page, and it will be enough for the lab exercise we are going to do in the course. In order to mention, there are other versions that allow you, for example, sensitivity analysis and reading of Excel files, professional that include optimization and vectors, and the DSS version that is the most complete version of benzene is the one that we have used to build the WILIAM model. And there are another version that is quite relevant is the model reader. Model reader is also free. With this version, you can read any model that it has been built on benzene, including the WILIAM model. So you will be able to use WILIAM model or whatever model as complex as you want with model reader. You only may open, read, and run. You cannot modify, but you can run, understand anything with model reader. Okay. Also, there are some VNAP runtime to run benzene application and some software for graphic interface. But the most relevant for you at the moment, at least, is the PLE free versions and the model reader. So this is the, let's say, the main frame of the screenshot of the benzene. When you open benzene, you will find something like that. And this is a model that example model with the rabbit population and how it appears in the screen. You have some tools to save, to cut, to copy the model. You can introduce new stocks, new variables, and you can in the left part you have some analysis tools like the three causes, like graph, mode, sensitivity, and so on. So this is something that you are going to learn in the lab in the last session of today, I think. This is more or less all for my part. Obviously, it's time for questions.
Thanks a lot, Luis. Was great, I think, as an introduction. So please, if you have some questions, we have 10 minutes. So Luis was really precise on time.
Perhaps I could ask, is there a difference visually in the PLE and the DSS? Because DSS is more complete, but does it also look a bit different?
Yes, there is some, as far as the DSS is the complete version and the PLE is just the simple version. You have not all the analysis tools. For example, in the PLE, you don't have automatic sensitivity analysis. So some of the graphs here you cannot see. This is for sensitivity analysis. And there are some issues that are, let's say, limited in order to develop the models. For example, you cannot read from Excel files. You cannot let me remember. You cannot optimize. Optimization is not allowed. And you cannot use external functions. And well, this is the most. You cannot read from databases, not only from Excel files databases. So it's a good tool, PLE, for learning and for simple models. There are a lot of simple models that you can develop. But if you need to do something more professional with vectors, for example, with external data and so on, you will need a professional version. Yeah.
Okay, thanks. There is Gianluca that raises hand.
Hello. Thank you for the presentation. I did not understand the main point of the presentation because I did not understand because why dynamics system modeling can explain well the causality relationship. I did not understand well the point of transparent of the model.
So this is the methodology of system dynamics. Methodology of system dynamics means that the starting point is just to use the causal relation. So you try to have the causal relation and you put into the model. Not that the model is plain. Well, obviously, if you use the causal relation to build the model will explain the causal relation. This is a feedback between that. The opposite, maybe let me explain with the opposite. The opposite is when you don't have this kind of causal relation implicit in the model. Let me explain. Do you know something about neural networks, deep learning, or something like that? Okay, if you are familiar with neural networks or deep learning, in these kind of models, you put together all the inputs and you show the model with the outputs they show. So internally, the neural networks obtain the best parameters to fit the relations between input and outputs. And maybe it's okay. Okay, you find a very good relation between inputs and outputs, but you don't know what is the causal relation between inputs and outputs. You only know that there is a mathematical model that it's okay, it runs and it fits, but you don't know why. This is but in dynamic systems, system dynamics, we try to do just the opposite. We try to start from this causal relation and we try to say, okay, I show some example. If we increase CO2, we know that temperature is going to increase. And we know because physical reasons, experts, and so on. So we are going to model this kind of relation. There are many kind of samples I can give you, but this is the main idea. So as far as we use like a starting point, the model is going to be transparent. Everybody will be able to check what is your point there. This is the issue. I don't know if we understand now.
Yes, I get it.
And this is very important. This is really very important. Maybe let me give you another comment. In the case of WILIAM, we have tried to be very transparent in all the points. And for example, we have something, probably Inigo is going to talk about that later, but let me give you in advance something. We try to be so transparent that all the data are in Excel files. So the model does contain any kind of number, a strange number or whatever. Everybody is reading from Excel files, scenario parameters, input variables, everything. So, for example, even if you don't modify the model, you can modify the data in the Excel file. You can check it and you say, okay, let me give you an example. In the scenario, we have considered that the fertility rate is 1.3, and you can check in the Excel file, fertility rate for this scenario is 1.3. So this 1.3 is what is going to be read by the model. So you said, no, it is not 1.3, it's 1.2. This is crazy. Okay, you only have to change this number, 1.2, and the model will run with 1.2 instead of 1.3. Well, I give you this simple example, but you can do it for all the parameters in the model. This is one of the, let's say, strong points in WILIAM model. Everything is transparent. And you can move, if you want, you can change any kind of parameter. This is transparency that I mentioned. I don't know if there are more questions.
So we have a few minutes. So just a comment, Luis. Transparent does not mean that it's simple, because
No.
after many years that I work in system dynamics, one of the most funny part of the work is to try to understand why you get some result, starting with the causal relationship that you build. And often after making a very nice discussion and argument to have a certain result, you discover that it was a mistake, like a plus or minus, something like that. But it's probably one part of the story that is transparent, so you can try to make this kind of argument.
Yes, especially in our case, it's especially complex because we have too many variables, too many relations, even when all the variables are accessible. But you are completely right. It's too complex to understand all the relations. Yes, you are right.
So Charles, please.
This is just building on Timu's question. If some of us were going to work on WILIAM itself, which Vensim license would you recommend, the professional one?
Well, as I said, in order to run WILIAM with different scenarios, different parameters, you don't need the professional version of Benzene. You can use the model reader, and you change the parameters in the Excel file, and you will obtain different results. Anyway, there is also a Python version of the WILIAM model. So we have translated all WILIAM to Python. So it's possible to work with Python version that you obviously don't need any commercial. The question is that the Python version usually is slower than the Benzene version, and we have usually updated versions of Benzene, and the Benzene translation, the Python translation, sorry, is just a little bit later. So some questions are not so. And
Luis, there are two questions on the chat that I think are interesting.
Sorry.
The first, no, don't worry. The first one is, okay, you say that WILIAM is not a black box model, but is the complexity a sort of barrier on understanding, reading, sharing it?
Well, I'm afraid it may be. Yeah, I'm afraid it is. Yes, I would like to say no, but maybe. So
the trade-off between the fact of trying to make a reliable representation of the society and the simplicity is not easy. I mean, to find a good balance.
That's right. Maybe if you focus the attention in a specific part of the WILIAM model. Let's an example. Imagine you are an energy expert, so you understand everything about energy, about all kinds of the mixed energy, how the energy is produced, the losses of energy, the transformation process of energy, whatever. So if you are an expert of energy and you go into the part of energy submodel of WILIAM, probably you will understand most of the things. Obviously, there are documentation to explain the equations. But if you are not an expert of energy transformation processes, maybe it will be more difficult to understand why this parameter, we have so many losses, or why you transform only one part of the petroleum in gasoline. And so it will be difficult to understand the details if you are not an expert on this area, because there are many details. For example, for myself, it's quite hard to understand the economic part of WILIAM. I should recognize I am not an economist, I am an engineer, and there are many equations that I said, this is crazy, I don't understand exactly. So it's difficult for one person to understand everything. And as you said, as much complexity you have, more, let's say, difficult to understand is the model, yes. It's a barrier to understand.
This is why multidisciplinarity is important, and probably Nigo will focus on it. Now, there are one question here again is, so there are some specific relationships that maybe are unclear. So the example that Lucas was making is about global energy consumption and GDP. So I mean, some relationship, of course, this depends. My answer would be, it depends on how the model. So if the model is clear, then probably you can represent clearly. But of course, some of them maybe are too simplistic.
Yes, you are right. Lucas is right. I use a very simple example about the relation between GDP and global energy consumption in order to start with a, let's say, simple idea that may be interesting for us. But you are right that it's not so clear. In the real WILIAM model, you are going to see the relations between the energy module and the economic module, and that what is clear is that as much GDP we produce, we have energy intensity. Energy intensity is just the energy we need to produce one GDP unit. With historical data, we need to consume more energy in order to increase GDP. So this is the historical fact. So we use this historical fact and this historical data in order to explain how is the increase of energy consumption if we increase the GDP. These relations is done through the energy intensity, and the energy intensity is not constant. It has been decreased along the years, so maybe we are more efficient with energy. But well, for example, for this example, we have different energy intensities for each of economical sectors. So the energy intensity of each economical sector is different, and the energy intensity is different for each kind of energy type. It's not the energy intensity is different for electricity, heat, fuel, or whatever. So and it has its own dynamics. We will need to get deeper into detail, but this is the relation. So by other way, as we have an economic sector for energy production and energy transformation and energy transport, this sector of the economy increase when there are higher consumption of GDP, at least these sectors, because they have to produce more energy. So they produce, let's say they obtain more money or whatever. Say this is the contribution to the GDP from at least the energy sectors. So anyway, I understand that this is not so clear, but well, we have this relation in the model.
Okay, just shortly, Lucas, if you want to make a point.
Yeah, I just wanted to clarify. So, but I think you answered actually my question. It was more relating to the fact that you can have a correlation that is quite clear between two variables, but that's not the same then as assuming a link of causality between the two. But I think you answered this now. So thanks.
This is the job, the difficult job of doing the model, let's say. And Leo, just quickly, if you can, because we are running out of time.
Yeah, maybe the question is too long and it will answer itself in the process. But my question is, what are the modes, or how do you derive the differential equations? You showed the system overview of the positive and negative feedback loops. And I think the model, this differential equations are not resulting out of this view itself, but you have to, as a modeler, you have to play around with the equations. Yeah, I'm not aware how you get up with the equations.
Well, this is a more difficult questions, because we will need, let's say, a long time to explain in each different case. But let me give you a general answer. We can have different cases. In some cases, let's say the easiest case is when we have a differential equation coming from the scientific knowledge. For example, the relation between energy and potential energy and energy produced, or maybe any kind of physical relation that is quite clear. So no problem, you can put that. The second situation is what there is no, let's say, differential equation in the knowledge area, because there is no clear, no mathematical relation. Let's say I have been talking about fertility. How is going to evolve fertility in the future? Nobody knows. Maybe you can hypothesize, have hypotheses about the fertility has relation with education level, maybe with the GDP, because richer countries has lower fertility rates, maybe with the age of working for women, if the woman starts soon or later to work, or you can formulate different hypotheses. So in order to contrast these hypotheses, you have at least two ways to contrast. One is just to consult with experts by themselves, or literature. So you find some papers that say, okay, there is a clear relation between fertility and the woman education. As higher is the woman education, fertility rate is lower. Okay, and this is by several experts, several papers. So you assume this relation and you try to put into the model. And maybe there is, and in order to give numbers, you use historical data to fit the best equation. The best equation according what the knowledge from experts or whatever you have, then you use historical data to fit this relation. This is more or less the general way to do the things.